a particle with moment of inertia I is executing rigid rotation in a plane. This means this is a 1 degree of freedom rotor. A possible state of this particle is described by the wave function. The functions which are contained here are the normalized eigenfunctions of LZ. There are 3 parts. In part A, normalize psi. It means find the numerical value of this n. And our normalization condition this is the general form. In this problem, these functions contain just one independent variable, phi. Therefore, when we apply that expression, normalization condition, to this problem, the integral is just one-dimensional integration. Integration is over phi. But it is not necessary to do any explicit integration because these functions are eigenfunctions of LZ operator. And as we just discussed during the last hour, eigenfunctions of a quantum mechanical operator are orthogonal. So, for example, such integrals here we have just one variable. What is the full range for phi? 0 to 2 pi. The value of this integral, you may do it explicitly by substituting this expression, all right? But you may also use the general principle that whenever m is different from m prime, the two functions are different. And therefore, they must satisfy orthogonality property, which means the value of this integral is going to be 0 for if m is the same as m prime, then it is the normalization integral for this function. In that case, this says the problem states that these are normalized. Look at the factor 1 over square root of 2 pi. This number is obtained by normalizing this function here. So, for m equals they are orthogonal and normalized. We had used a term to describe both of these, both normalized and orthogonal. What was it? Orthonormal. So we say these functions are orthonormal. Now, we use the orthogonality property and normalization property of these functions to evaluate this very, very clearly. We select n as a real number. So we have n squared, then 2 times I'm putting these star symbols because these are complex valued. This is the integral. All right. You may make it completely explicit by substituting this expression. But it is not necessary. Now, to do the integration, you have to expand. So how many, when you multiply this part with this part, how many terms will be added? 2 terms in this factor, 2 terms in that factor. When you expand it, how many terms are going to be present? 4. Therefore, we are talking about 4 integrals which are added. Now, for the 4 integrals, let us first eliminate the following. One of the 4 terms will be by multiplying this function with that function. And it's an integral. But this function is different from that function. Therefore, value of the integral is going to be 0. Similarly, of the four integrals, one of them will be this function, phi minus 3, multiplying with phi 3. This integral is also going to be 0. There remains two more. One of them is this times that, but they are the same functions. And therefore, the value of the integral is going to be 1. Similarly, this function multiplied with that one, again, same functions. The value of the integral is going to be 1. In general, as a result, because of the orthogonality property, only non-zero integrals are, when you expand, the products which contain the same function. So, the value of this integral, non-zero part is this times that, 2 times 2 is 4, don't forget. Plus this times that one, minus 5 times minus 5 is plus 25. These are the non-zero integrals. But this integral, value of this integral is 1. It is given to us, we are told. Value of this integral also 1. Therefore, the value of this integral is 4 plus 25, 29, and so we have n squared times 29 equals 1, which means n is 1 over plus or minus 29, and as a convention, we take the plus sign. N is 1 over square root of 29. Second part, write the Hamiltonian. Of course, H but in this is not the full two-dimensional, 2 degree of freedom rotor. It is a 1 degree of freedom rotor. Therefore, only one of the components of angular momentum is non-zero. Only the z component if the plane is xy plane. So this is we can write it explicitly. LZ operator is minus I times h bar times first derivative with respect to phi. This is square of it. When you take the square, this is just a constant. Square of this constant gives you minus h bar square. Remember, minus I times I times minus I is same as plus I times plus I. I square is minus 1. So minus h bar square. Square of this operator, this is the first derivative operator. Square of a first derivative operator is second derivative operator. So this is, therefore, minus h bar square divided by 2i times the second derivative with respect to phi is the explicit Hamiltonian for this rotator. Is psi an eigenfunction of this Hamiltonian? Let us use this part in symbols. What is psi? This n is not important for showing whether it's an eigenfunction or not. So let us take also this factor minus or 1 over 2i is not important for showing whether psi is eigenfunction of Hamiltonian or not. Why? LZ square commutes with Hamiltonian. And therefore, they must have same set of eigenfunctions. Which means if I show if it is an eigenfunction of LZ square, it will also be eigenfunction of 1 over 2i times LZ square. So 2 times phi 3 minus 5 times phi minus 3. And the question is, yes or no, constant times the same function. If the answer is yes, then we will conclude that this expression is an eigenfunction of LZ square and therefore eigenfunction of H. If the answer is no, we are going to say it is not an eigenfunction. Now, to do that, we apply. This is we are told that these functions are eigenfunctions of LZ. What does it mean? Operator function, constant times function. These are eigenfunctions. What are the eigenvalues? H bar m. The same functions, these functions, are also eigenfunctions of square of LZ. Why? Because any operator commutes with all of its powers, including square. It could have been third power, fourth power, fifth power, or any combination of powers. C1 times first power plus C2 times second power commutes, which means that any such expression, all such operators have the same set of eigenfunctions. These functions, phi m, are also eigenfunctions of LZ square. So if you apply them, eigenvalue of the square is h bar m squared. So here we can replace this with m is 3, take the square, 9 h bar square. Here m is minus 3, take the square, also 9 h bar square. Okay. Now we see that 9 times h bar square can be factorized. This is 9 times h bar square times phi 3. This is times phi minus 3. Nine times h bar square. Remember, I did not include 2. I need this 2 because I have to compare with this, with the right side. 2 times phi 3. And also there is this minus 5. All right. This is the simplified form of operating as z square on the function. All right. Now, I compare this expression with this expression. What is my rule? Operator function equals a constant times the same function. This is what we mean by eigenvalue, eigenfunction equation. F is called eigenfunction of operator A, and K is the eigenvalue. So, when you compare this expression with this one, what is your answer? Is this a constant? 9 times h bar square. Is this expression same expression as this one? Yes. Therefore, does this expression is the left side equal to a constant times the same function? Yes. What is the value of the constant? 9 times h bar square. Therefore, the eigenvalue is 9 times. The answer is yes. Eigenvalue 9 times h bar square. This means eigenvalue so we conclude that this expression is an eigenfunction of LZ square. And the eigenvalue is 9 times h bar square. But the problem is asking us, is psi an eigenfunction of h instead of LZ square? But h is 1 over 2i times LZ square. Okay. So that expression, constant times operator, always commutes with the operator, which means any eigenfunction of one of them is also eigenfunction of the other one. Only the eigenvalue will change because of the multiplicative constant. Eigenvalue of h, which is E for this state, is 1 over 2i times 9h bar square. This 1 over 2i is the relation between Hamiltonian and LZ square. They are very simply related. 1 over 2i times LZ square. Finally, is psi an eigenfunction of LZ itself? We have shown that it is an eigenfunction of LZ square. Normally, we would expect this expression to be also an eigenfunction of LZ. However, it's not it is not true because of the following reason. The expression contains two functions. One is phi 3, the other is phi minus 3. Both of these functions are separately are eigenfunctions of LZ, separately. But this expression contains a mixture of phi functions. One is phi 3, the other is phi minus 3. M equals 3, M equals minus 3. All right? And so whenever there is a mixture of eigenfunctions or a linear combination of functions like this, it cannot be an eigenfunction of the defining operator. But we can show it. LZ Now this one we can replace using the relation here. M is 3, so this is 3 times h bar times the function 3. This one also using the same property, but this time m is minus 3. Minus 3 times h bar times phi minus 3. Now, there is no common number in both factors. One of them is plus 3 times h bar, the other is minus 3 times h bar. So, I cannot factorize. I mean, if I can factorize plus 3 times h bar, but it will change the function itself. No such problem was present here because this was a square. So that a square of a plus number is the same as square of a minus number. So that 9h bar square could be factorized without changing the function. But here, there is no such property. If I factorize this 3h bar only, I will get 2 times phi 3, but there is a minus here, This will become 5 times phi minus 3. All right? Now, when I compare this, okay, is this expression, which is the left side here, does it satisfy the right side here? Okay, there is a constant here, but is this expression same as that one? No, because this has a plus sign here, this has a minus sign there. Therefore, does this expression satisfy LZ psi equals constant times psi? The answer is yes or no. Which one? No. Therefore, this expression for psi is not an eigenfunction of LZ. Another question. The topic here is not covered, it is not included, but we may still do it. This time there is a particle rotating in three-dimensional space, which means a 2 degree of freedom rotor. It is said that this particle is in a state described by this wave function, which is 0.4 y3. Let us put this. This is L. This is M value. Sometimes the following notation is also used. L is the L index is written as a subscript, and the second index is written as a superscript. This notation is also used. This way, you may separate L value from M value maybe more easily. But I think this notation is also as simple as this one. All you have to remember is that the first index is L, the second index is M. And in my notes, I have used this notation. Plus C times and these functions are the standard spherical harmonic functions we just discussed. The first part of the problem is similar to the last problem we solved. Exactly similar. It says, what should be value of C for psi to be normalized? General normalization condition. Number of integrations is equal to the number of independent variables. In our previous problem, it was a 1 degree of freedom rotation, rotor. There was only one variable. What was it? Phi variable. But this is a 2 degree of freedom rotor. It has how many variables? 2 variables. So this is a double integral. But number of variables is not so important for such problems. Why? I have repeated maybe tens of hundreds of times up to now. Whenever you have a set of functions that are eigenfunctions of the same operator, then these functions satisfy orthogonality property. And if you are also told that those functions are normalized, then we will say that such functions satisfy orthonormality property. And the standard spherical harmonics satisfy the orthonormality property, which means the standard spherical harmonics are already normalized, and they of course satisfy the orthogonality property. So we take these functions. I assume C to be a real number. Otherwise, I would have, if I assume C to be a general number, then it could be complex valued. In that case, it was necessary to write C star here. But for simplicity, I'm going to assume C to be a real number. Now, how many integrations are involved here? 2 integrations. These are double integrals. Because number of variables is how many? 2. The expression for theta is the expression I had written down during last hour. Sine theta d theta times d phi. Limits of integration for theta 0 to pi, for phi from 0 to 2 pi. All right? But none of these is needed to do this problem, because we are going to use the given orthonormality properties. When you expand 2 terms here, 2 terms there, how many integrals are going to result? 4 integrals, right? Because there are 2 terms here, 2 times 2. There are going to be 4 integrals. Some of the integrals will contain a product of different functions. For example, y30 times this function, y2 minus 2 function. These functions are different functions. And during the last hour, I had written down the property that the value of the integral, like this, unless both L is L prime and also M is equal to M prime. In that case, the value of the integral is 0. Now, this function times that one. The L's are different. One has L equals 3, the other has L equals 2. That is enough to conclude that the value of that integral, like this, the value of this integral is, what is it? Orthogonality. It will be 0. This property. This is one of the integrals. This is one of the integrals when you expand it. Another such similar integral is if this function is multiplied with this one. Again, the value of the integral is 0. There remains only two non-zero integrals. What are they? When you expand them, only the same functions are contained. Yes, like y3 0 times y3 0 d tau. The value of this integral is 1 because the standard spherical harmonics are already normalized. This is one of the non-zero integrals. Another non-zero integral is this times this. This is also one. So the net result is, because of the orthogonality property, the result of the such integration, only the diagonal terms are non-zero. We separate diagonal from non-diagonal. Diagonal means row number and column number are the same. Otherwise, it's non-diagonal. So in this case, if the same function is present in the product on the other side with this index 3, 0, only that integral is non-zero. And we just, but don't forget the coefficients. So we have 0.4 times 0.4 square times the integral, which is equal to 1, plus c times this term times that term, it gives c square, times the integral, this integral, which is equal to 1. So the net result for the integral is this expression, but the normalization condition requires that the result should be 1. So this is a relation, an equation, and this equation contains how many unknowns? One unknown. What is the symbol for the unknown? C. 0.4, that's fixed number. 1 is fixed number. The symbol for unknown is c square. So we have c square is equal to 1 minus 0.4. And then you get, so you may select c as either plus or minus square root of 0.84. Both, there are two answers here. Even when we assume c to be a real number, we have two answers. Can you consider this C as a normalization constant? No, because a normalization constant has this form. It multiplies everything. But that C is multiplying just one term in the linear combination of expression there. All right? C is not a normalization constant, it's a coefficient. And the, whether the sign of the coefficient, such a coefficient is plus or minus, could be important because it will change the function. On the other hand, sign of normalization constant, because normalization constant is an overall multiplier. The sign of normalization constant is never physically significant. It could be either plus or minus, nothing changes. But that one, the situation over there is different. Let us continue with the problem. What is the average value of L square of this particle in this state? Let me write this value is here. Average value of L square, definition, it is this. Now, we simplify this part first. I'm going to replace C with the number later, but just keep in mind C is either plus or minus 0.84. C times y, 2 minus 2. Then I will expand. Operators never do anything to numbers, only to functions. So you can factorize constants. Now we simplify these. But spherical harmonics are eigenfunctions of L square operators. They satisfy okay. Now, in the first term, what is the value of L? You read it from the subscript. L is 3. 3 times 4 makes 12 times h bar square. So this can be replaced with 12 h bar square times same function. L is 3. 3 times 4 is 12 times h bar square. A similar simplification can be done over there. Here, what is the value of L? L is 2. 2 times 3, 6. This can be replaced with C times 6 times 6 times h bar square times okay. Now, also multiply with 0.4. and this one, c times 6 times h bar square. This is the full simplified expression which removes the operator. Everything is scalar here, just functions. Then we multiply from the left, which is, in other words, 0.4 y3 0 complex conjugate plus c times y2 minus 2 complex conjugate. Multiply this simplified expression. Maybe let us, 4 times 12 is 48, so this is 4.8, isn't it? H bar square times y30 plus c times 6 times h bar square times y2 minus 2 into d tau. Now the problem becomes similar to what we did in normalizing the function. There are, how many terms are there here? 2 terms added. Also 2 terms over there. When you expand, how many integrals are you going to obtain? 4 integrals when you expand. Now, 2 of these integrals will contain different functions. And when you integrate, the result will be 0 because we know that all these functions satisfy orthogonality property. The other 2 functions, integrals, will contain the same function. For example, it will contain y30 conjugate times this function. And the value of that integral is 1, because we know spherical harmonics are normalized. So the final result is just the coefficients, 0.4 times 4.8 times h bar square and the times an integral, which is the integral of this times this function. The value of that integral is 1. Then this times that, which is c times c square times 6 times h bar square times the integral, which is also equal to 1. So this is our final result. Now we put c square. C square is 0.84. And then add up, and you obtain the final answer, which is the average value of square of L in such a state. The final part here was what is the average value of LZ? Instead of L square here, you are going to put LZ. Then you will simplify LZ psi as I did it for L square. But remember that spherical harmonics are eigenfunctions of LZ, but only m is involved. This is h bar times m. So when you put LZ here, m is 0. So if this were LZ, it would be, because m is 0, the overall thing would be 0. Is that clear? And in the second term, m is minus 2. When you apply with LZ instead of L square, here the result would have been minus 2 times h bar. And then the remaining part is exactly the same as in L square. All right, we stop.